Right, here are the class notes for objectives E2 and E3. We're going to be looking at graphs of the basic rational functions being 1 over x and 1 over x squared, and then transform those. So the first function we're going to look at 1 over x. Here's a table and its graph. It has these two hyperbolic shapes that we can see over on the right. It fits in between a couple of asymptotes. So a hyperbolic shape will be one that has linear asymptotes. Thing over there on again, the graph that we're looking at on the right. And we can get its values by simply taking the reciprocal of whatever x is. So if x is 2, then our function value is 1/2, as we can see by this yellow option over here on the table. Or if x is 1/3, then its reciprocal is 3. So as x gets close to 0, we end up with large numbers for y. And when x becomes large, y ends up being a small number, a number that's pretty close to 0. So again, written out here, we can see that as x gets large, f of x gets really close to 0. As x gets close to 0, then f of x gets really big. But if we approach from the negative side, we'll see the same numbers show up, except our answer comes out negative instead. So if x gets really small, meaning x goes really far to the left on the graph, then our function still gets really close to 0. But if x gets really close to 0 from the negative side instead of from the positive side, then f of x still gets really big, but it's negative this time. Now, because we never actually get to 0, either for y or for x, we have asymptotes in this function. We're not allowed to plug in 0 for x, because you can't divide by 0. That'd be bad. We get no solution if that happens. But also, no matter how big x gets, no matter how far out to the right we go, right or left, our y value is never going to hit 0 either. Reciprocal of a really large number, while close to 0, is never actually going to be equal to 0. So it gets those two asymptotes, y equals 0 and x equals 0, shown back up here in the graph. Now, a big thing out of this section is going to be this arrow notation shown off over here. And effectively, what this arrow notation is about is a way to not exactly set x equal to a number, but say I really would like to set x equal to some number, in this case, say a, but maybe I can't do that for some reason. How can I still talk about x being equal to that number without actually having to be equal to it? To give you an example, in this problem, I'd really like to set x equal to 0, but I can't actually do that because then I would divide by 0. I still want a way to talk about what's happening if x were to be 0, but since I can't set it equal, I've got to do something else. So instead, we'll introduce this arrow notation idea. We'll say as x approaches 0 or whatever number I might want to have it approach, and then figure out what number y approaches when x does that. So again, it's a way to just avoid having to set x equal to a number when I still want to talk about what would happen if x were equal to that number. To skip ahead in the notes a little bit, I want to take a look at limits, which is going to be all the way at the end. And graphically, another reason why we might want to talk about this limit or this idea of x being not exactly equal to, well, something like, but not necessarily equal to some number. How would we go about doing that? Because if I look over on this graph to the right, and I'm looking at the spot that's highlighted in purple, this point over here on the right, I can look at the graph and I can see that if x is -2, y is supposed to be 3. I can look at the graph, I can see it's all going to that point, but for whatever reason, I have a hole in the graph instead of having it filled in. I'd still like to be able to talk about that hole and where it exists and how it might fit into the function, but I'm not allowed to plug in -2 for x, because if I do, I'm going to get no solution. So instead, I want to talk about x approaching 3. I want it to get really close, or I want to talk about x approaching -2, this part over here. As x approaches -2, where is y going? I can clearly see I should have the point -2, 3, because that's what the graph is doing. But since I'm not allowed to set x equal to -2, I have to get a little bit creative and instead take a limit as x approaches 2. And then say, okay, yeah, y has got to be 3. So that's why we're going to be introducing this notation, as we can talk about numbers that we're not technically allowed to plug in or set equal to. So we have this arrow notation, something like, but not necessarily equal to that number. The other graph we'll look at and start applying some of this notation to is the square reciprocal function 1 over x squared. So if I go to look at the graph of this function, the negatives aren't going to matter anymore since I'm going to be squaring whatever x value I plug in. So it no longer matters if x is 2 or -2. 1 over 2 squared is the same as 1 over -2 squared. It's 1 over 4. And also, if I'm going to take the reciprocal of 1 over 3 squared, I'll end up with 9. I can see the pattern emerging in those two shapes, or in those two sets of the table, and the graph over on the right. Similar looking shape to the previous one, except now both of those hyperbolic shapes are positive. They're both above the x-axis. So from that graph, I want to identify a couple of things, both a vertical asymptote and a horizontal asymptote. I can see them sketched in on the right, but I need to give them equations. That vertical asymptote is the line x equals 0. I know it's a vertical line, so it should have the equation x equals something. So x equals 0. And then my horizontal asymptote is that flat line. It is the equation y equals 0. So with asymptotes, and it's important that those both come out to be equations. Then with all of these next few questions, I want to use my new arrow notation that I just brought in. So this first one is asking, what happens to the graph if I try to let x be equal to 0? I'm not technically allowed to plug it in, but I can say, well, let's look at what happens if x gets close to 0. First one is going to ask us to approach from the right side. So I'll start along the right part of my graph and go up. And I can see if I do that, x is headed toward positive infinity. The other one is going to ask me to look at approaching 0, but this time from the left. Start over on the left side and trace my graph in, and I am again headed up to positive infinity. The next two sets are going to ask us to look at what happens if x becomes really large. It's effectively asking us for the end behavior of this graph, what happens all the way to the right, and then what happens all the way to the left. And in both of those cases, our graph is approaching the horizontal asymptote, y equals 0. So if I go back to fill out our domain, we already have domain written in. That domain is everything, or every real number except for 0. So I'll write in my domain is all real numbers except 0. And that's how I'd write it out. I would just take the union of the two intervals, one that's above 0 and one that's smaller than 0. Another way to think about this domain as being all real numbers is I'm going to start from the all real number set, negative infinity to infinity, and then simply remove 0. So I'm going to go up to 0, stop, and then start immediately after 0 and keep going. The range on this one, though, unlike the last one, is just a single interval. It's all positive numbers and none of the negative ones. Then a helpful way to think about uh, transform or finding other rational functions is to think about whether it looks like 1 over x or whether it looks like 1 over x squared, and then transform it with our linear transformations. So if I start from the graph of 1 over x to get the graph of 1 over x minus 4 minus 1, well, I'm just going to take my old graph and shift it 4 units to the right and 1 unit down, which means that my new asymptotes, one of them will be a vertical one, the other a horizontal one. That vertical asymptote is now going to be at x equals 4, and the horizontal asymptote at y equals -1. And I would go just graph those two asymptotes first. So x equals 4 is right there, and y equals -1 be right here. And then I can plot my new graph. It looked like 1 over x, so I'll be sure to make a graph that still has that same shape, but just fits in between my asymptotes. Coming back to look at our arrow notation again, I want x to approach 4, both from the right and from the left. If I start on the right side, I'm headed up. But if I start on the left side, I'm headed down. So I'll get negative infinity if I start from the left side, but positive infinity if I start from the right side. For our end behavior, looking at what happens to the graph on the left and on the right, both of those sets are going to approach the horizontal asymptote, which is at y equals -1. So g approaches -1. And for our domain, it'll be all numbers except for 4. An interval notation written like that. While the range will this time be all real numbers except for -1. To transform another one, this time we'll start from 1 over x squared to get to the new one, 1 over x plus 2 squared, and then -3. This one's going 2 units to the left, and this time 3 units down. And again, I'll sketch in my asymptotes first. One of them at y equals 3, and the other at x equals -2. I guess I skipped a step in the notes, but that's okay. And then fit my graph around my two asymptotes. Since this one was squared, they should both be above the x-axis, or rather above our horizontal asymptote of y equals -3. So those two asymptotes are at x equals -2 and y equals -3. As x approaches the vertical asymptote, the function will shoot up to positive infinity, while when x becomes a very large number, whether positive or negative, our y value is going to approach -3, that horizontal asymptote. Our domain should be every number except for -2, and our range will be all of the y values greater than -3. This time I'm writing them in inequality notation instead of an interval notation, just for a change of pace. All right, so if these two graphs are transformations on 1 over x and 1 over x squared, and I wanted to come up with equations for those two, well, all I need to do is find my asymptotes. So if I come to take a look at this first one, it's got a vertical asymptote here and a horizontal asymptote right here. I can just look at the graph and figure out where those asymptotes are. That horizontal asymptote was at y equals -3, while the vertical one is at x equals 2. So my graph, which looks like a 1 over x graph, rather than 1 over x squared, must be 1 over x minus 2, and then -3. If I apply that same idea over to the right, where I first locate its asymptotes, well, I can see my first one, my vertical asymptote, be right here, while the horizontal asymptote must be this line right there. That should be the equation y equals 4 for the horizontal one, and x equals 2 for the vertical one. I'll again write down an equation. This one should look like 1 over x squared, since both of those hyperbolic shapes are on the same side of the horizontal asymptote, but this time it's going down. So I must have a reflection in this graph. So I'll have -1 over x minus 2 squared, and this time +4. Now I will fill out the rest of this example later, so check the written notes for example 5. All right, looking at some limits. So if I take a look at this function, x squared minus 4 over x minus 2, I could quickly see that this thing is going to simplify. Let me just do that real quick. X squared minus 4 is factorable to x minus 2 times x plus 2, and it's divided by x minus 2. And then I have a factor of x minus 2 in both top and bottom. So this thing reduces to just x plus 2, but with the caveat that x is not allowed to be equal to 2. Since if I plugged 2 into the original function, I'd have a problem. I'd divide by 0. That's not so good. But if I were to try to graph this thing, it should just look like the line y equals x plus 2, because that's what it simplifies to, with a problem right there. This point in the graph, it's at 2, 4, because I can look at the graph, I can see that when x goes to 2, y is supposed to be equal to 4, except I have a hole there because of the way that my original function was written. I'd still like to be able to talk about the graph when x is 2, but if I'm only allowed to use equality, I can't really say anything. I would just have to say that f of 2 does not exist, even though I can look at that thing and see f of 2 is supposed to be 4. In order to still be able to say that, we're going to bring in this idea of the limit. That's this expression down here. It's the thing I talked about right at the beginning of this video. I want to be able to send x to 2. I want to effectively be able to talk about what happens when x is equal to 2 without the burden of actually having to be equal to 2. So instead, we'll say we have this limit. We'll look at x approaching 2. And, if x is very, very close to 2, then y is going to be very, very close to 4. And again, we want to use this in place of being able to say that f of 2 is equal to 4. Because we're not technically allowed to do that, but I still want to mention that point in some way and have some kind of mathematical way to talk about it. That mathematical way is the limit. So if I were to try to apply that to an example here, I can see this point right here. If I'm looking at the graph, the function is supposed to go to 3 when x is -1. All right, and just follow my graph through. It's clearly headed to that point, -1, 3. So the limit of this graph as x approaches -1 is 3, because that's where the graph is going. However, the actual function value is defined at this filled in point right over here, just down below. So g of -1 is actually equal to 2. So the limit and the value of the function don't always have to line up. In fact, oftentimes when we look at the limit, it's because some sort of problem with the function value has arisen. So we want to be able to say something about the graph without having to look at the point directly. So that'll be a common theme when looking at these limits. As a fun side note, when the limit and the function value do match up, we say that the function is continuous. So this particular graph is not continuous when x is equal to -1, because the graph function value and the limit value don't line up with each other. So one-sided limits, the previous thing we were looking at was what we call two-sided limits, or just the limit. A one-sided limit just lets us break that down and look at approaching a number from either side. We were doing this already when we were looking at vertical asymptotes. We'd look at approaching the vertical asymptote from each side and then see what's happening to the graph. We can also do that with some other functions that maybe don't line up completely, like this graph that we have here, the absolute value of x minus 2 over x minus 2 has what we'd call a jump discontinuity at 2. Because if I look on the right side, my graph is equal to 1, but if I look on the left side, my graph is equal to -1. So if I try to just take a limit as x goes to 2, how would I know which number to go to? I don't know if I have to go to 1 or -1. And if there is that question happening, if I don't know which number I'm supposed to go to, it means the limit does not exist. I need both sides to agree with each other in order to have the limit in a way that I can talk about it. Since that won't always be the case, we'll break this idea down further to talk about single-sided limits or one-sided limits. Basically the approach from the right and approach from the left, and see what happens either side. So I can see on this graph, if I approach from the right side, I'm going to get +1. If I approach from the left side, I'm going to get -1. So the limit itself doesn't exist, but I can still look at their one-sided limits. To see that in practice, let's try to do 4 things for x equals 2 in this graph. So I want to take a right-sided limit and a left-sided limit, try and resolve that, and then also look at the function value itself. Well, if we approach from the left side, I would start somewhere to the left of my point and come into it, and I get -4 as my limit, because that's where the graph is headed if I start on the left side. If I start on the right side instead, pick some point over to the right of my point in question and come into 2. I can see on that side, my graph is headed to 3. Now, because those two limits don't agree with each other, the function value itself does not exist. So I'll put dne for the full limit or the two-sided limit. But then if I actually plug in 2, I get a completely different number up here at 5, because that's what the graph is filled in. So this is another example of a very discontinuous function. Nothing about this thing is continuous. Finally, I'll introduce the infinities into the limit idea, and we were really doing this earlier with our arrow notation. We'll just be more formal about the statement this time. So anytime x approaches an asymptote or a vertical asymptote, anytime x is going to approach a vertical asymptote, our limit is going to be one of the infinities, either positive infinity or negative infinity. If I approach the asymptote and I go up, that'll be positive infinity. And if I approach the vertical asymptote and go down, my limit will be negative infinity. So I can see on this graph, heading toward my vertical asymptote from either side leads to positive infinity. Meanwhile, the other way I can look at these infinite limits is to take a limit as x itself approaches one of the infinities. And that's effectively asking us for the end behavior, similar to how we looked at polynomials, except a lot of these rational functions are going to have some asymptotes that dictate its end behavior. So, and now to return to the example we looked at briefly at the beginning of the video, let's take this graph over here to the right and look at 3 key x values. I want to look at -4, which is going to be this point right over here. I want to look at -2, which will be the example point we used. And then we're also going to look at +1, which is where that jump discontinuity is. So we're going to look at both of these two spots in the graph. Cool. So let's start with the example, the one that we already did, the one where something interesting goes on. Sending x to -2. Well, it doesn't matter if I approach from the left or the right side, they both head to the same point, which is at 3. So my left side, my left side and my right side and my limit as a whole all agree on the y value is supposed to go to 3. However, function value itself does not exist because there's a hole if x is equal to -2. So I can't plug in -2, so instead I need to use the limit to talk about the point, and that's our main motivation for why we're even looking at these limits in the first place. Can't plug in the number that I really want to have, so I'm going to pretend I can and see what the graph is telling me to do. Meanwhile, we look at the blue point, sending x to -4. Well, both sides agree. The limit should be 0. And also, if I plug in -4, which I'm allowed to do, I still get 0. Most points on a graph are going to be this case, where there's no difference between evaluating the function at 0 and looking at the limit as the graph goes to that number. I think I said 0 a second ago and I didn't mean to. So let me try that again. Most points on the graph are boring, like this one, where the function value and the limit just agree with each other, in which case there's no difference between them. We can see that here in the blue point, every single answer out of the 4 was 0. Not really worth talking about limits there, at least not right now. Perhaps more on that in a later semester. But for now, the limit was just as good as the function value itself. Because, again, the graph is continuous at -4. As long as the graph is continuous, the function value and the limit value will just be the same thing. So we tend to only look at limits when there's some sort of continuity problem. All right, well, enough beating around this other point. Let's see what happens if we try to send x to -1. So if we approach from the left side, that's the part where I'm drawing in purple, start from the left and come into 1, well, x, the limit there is going to be 6, since that's where the graph is going. However, if I start from the right side and come in, starting from the right and heading into 1, well, now I'm approaching this whole point where y is 3. Because those two one-sided limits don't agree, the limit itself does not exist. Nothing else I can have here. But since one of my points is filled in, I can actually evaluate the function at 1, and it's just 6. That top point was filled in. Now, using our limit notation to represent the behavior of f around x equals 2, well, that is my vertical asymptote right over here. So what's going on? If we try to send x to 2, well, first of all, I can't plug it in because there's an asymptote there, and that's a problem. So I'm not allowed to plug in 2 for x, but I can take a limit as x goes to 2. And that limit would be -infinity because we're going down. Because the two sides agree with each other, I don't need to split it up into its two parts, although I could look at approaching from the left and from the right. But they're headed to the same place, so I get to talk about the full two-sided limit here. That two-sided limit is -infinity. And that's the end of units E3 and E2.